So today we continue the previous topic discussion is the semiconductor electronics material devices and simple circuit. Okay. So previous class end here. Okay. So previous class end we discussed the extrinsic semiconductor, means called impure semiconductor, means some added some impurities. Suppose it's called doping, or these are called some pentavalent atom or called trivalent atom. We get some n-type semiconductor and get a p-type semiconductor. Okay. So we get some majority carrier and minority carrier. Okay. So in p-type semiconductor we get, in case of p-type semiconductor, so majority is whole, majority carrier is whole, and there is a minority carrier. Minority is called electron. And for n-type semiconductor, n-type, so majority is electron and minority is whole. Okay. So now due to that some doping. Okay. So now update that energy band diagram. Okay. So due to doping we get some extra energy level. Okay. So due to that doping, we get extra energy level. Okay. Due to that doping. Okay. So that's the doping is called ED and EA. There's a energy level here. So that's the doping is look like. So that's the conduction band, and this called a bottom part of the conduction band is called EC, and there is a valence band here, and the top part of the valence band is called EV, and that's the energy gap EG. Okay. So now that the extra energy level is called ED. Okay. That's the energy level here near to the conduction band. Okay. And this called ED. Okay. And this called here is a donor impurity. This for donor impurity. Okay. So we added some donor impurity here, some extra electron, and if there's this gap from ED to EC, that's a very small. Okay. Suppose approximately this value will be 0.01 EV. That's a very less than EG. So electron in ED so easily jump into conduction band. And we get some electricity, a conduction here. We get some electricity. Okay. So, so the element added to the donor to increase the electrical conductivity of that donor. Okay. So here the element added to donor, the element added to donor, okay, to increase the electrical conductivity, to increase the electrical conductivity, means, so if I dope by the pentavalent atom, so we get some extra electron here. So that extra electron are in ED. Okay, are in ED, and if the electron are in ED, so that electron easily jump into conduction band. So we get some good electrical conductivity here. So that's called a donor impurity. That's called ED. Now here is some acceptor impurities here. Okay. And acceptor impurities are in near to that valence band. So if I draw the diagram again, there's a conduction band. These are the lowest part of the conduction band. This is called EC, and that's the EV. There's the highest part of the valence band is called EV. That's the valence band. Okay, and here is some extra energy level EA, there's a near to that. See, these EV are right in EV. Okay, EA. Okay, these called acceptor impurities. These are called acceptor impurities. Now you see that the gap, that's the EG, and this gap, this is very small compared than EG. So electron, suppose we say that is a 0.01 EV. So electron from valence band, so easily jump here in EA. Okay, easily jump here. And if the electron jump from EV to VB to EA, so you get hole here, you get some extra hole here, you create a hole. So due to that acceptor impurity, we get some hole here. So because this gap is very small, and this hole here is a majority carrier here, and this is a donor. This is a majority carrier is for electron, and this is a majority carrier. We get some hole. Okay, so that's mean the here important. Okay, so Ne, and here that is a NH, number of hole, and NH here hole, and here the Ne, number of electron in thermal equilibrium. Okay, so number of hole and number of electron in thermal equilibrium, number of hole and number of electron, if I multiply these two, you get Ni square. What is Ni? Ni is the intrinsic carrier concentration. Intrinsic concentration. Okay, that is NH into Ni, we get NH into Ne, we get Ni square. Okay, that is the intrinsic carrier concentration, and this was due to the thermal equilibrium. Okay, that's a basic idea in our class 12. Okay, do not jump to the more complicated, complex or detailed concept here. That's the basic concept. So Ne is the number of electron, mainly carrier here, and NH, that's the number of hole. That's also the carrier. Electron is a negative and hole be the here be the positive. Okay. So now jump into the next concept we discussed, that's called a junction. Okay, the formation of PN junction, that's very important concept. That is formation of PN junction is very important. Okay, so and you see that you draw, this is at P region, and that is called N region. Okay, so these are the, and if P region, we know that P type semiconductor, and that's the N type semiconductor. Obviously these two are the extrinsic semiconductor, and you know that the P type has the majority carrier with a hole and minority with the electron. So there is some huge number of holes here. There's the holes here. Okay, and the minority here, say that is minority is electron, and here in N type there is a majority is electron. Okay, majority is electron, and there is a minority is a hole. Okay, and here if I close between these two types semiconductor, due to that concentration gradient of majority carrier. Okay, here you see that as a majority carrier is a hole, majority carrier hole, and here is a hole concentration is P type is more and less in N type. Okay, hole is majority. Okay, concentration of hole is more in P type, less in N type. And similarly, there's a N type has a majority carrier being that is a majority is a electron. So the concentration of electron in N type is more than P type. So due to that concentration gradient, due to that concentration gradient for of majority carrier mainly. So we get some current. Okay, so there is two types of current. Firstly, I said that is a one is a majority carrier current, and is called a diffusion current, and other current is a drift current. So let us we discuss what is a drift and what is diffusion. So if a concentration gradient, so see that the hole cross that this junction and goes in that direction, and electron from N to P direction. Okay, so now the diagram now look like this. Due to the concentration gradient, I will get a new diagram. So here you get a huge number of hole, okay, and here with a huge number of electron, because that's the p type, that's the n type, and these hole diffuse towards n type, okay, n type, because hole is a minority here. So here hole diffuse p to n direction, and here suppose here you get hole, and here it gets a huge number of electron, obviously. Okay, there is a huge number of electron, less plus. So hole diffuse in that region. Okay, here is a hole diffuse here. Okay. So there is a hole here. Okay, and now you see that similar concept, electron diffuse from N to P. So electron diffuse N to P, N to P in that direction. So here electron here. Okay, and here is a plus, obviously, huge plus in p type, less in minority, mainly in the plus. Okay, so due to that the concentration gradient, electron diffuse n to p and hole diffuse p to n, and it create a barrier here, create a barrier here. Okay, yeah, barrier here. Okay, okay, don't be confused here. Okay, and now here we see that due to that diffusion, okay, so the majority, mainly there is a majority carrier. Okay, so here you see that carefully, this region is called depletion region. Depletion region. This region is called depletion region, and a junction depleted in the region. These are depletion because the junction depleted in this region. Okay, so here you see that in depletion region, okay, due to the concentration gradient, you get some depletion region. So here is in depletion region, this left side of this depletion region, we see that there is a huge number of electron here. Okay, and in right side we get huge number of hole here. So create a space charge region. So this depletion region is a space charge region, space charge region, and there are two types of space charge region. There's a negative space charge region, that's a positive space charge region. These are the negative space charge region, and that's the call this side is called positive space charge region. Okay, so there we get some two space charge region here. So due to that, now we draw again a diagram, the same diagram again. there is some electron, here is some hole, positive charge. Okay, in space station we get generate some electric field in that direction. Electric field. Okay, so due to that electric field, okay, so in p type, that's the n type. Okay, so magnetic area of like a hole in electron in p type, magnetic area electron in p type move in that direction, move in opposite direction of the electric field. So here we see that uh, uh, electron from p side to drift n side, p side to n side, due to that electric field, due to space charge region, so create some electric field, and due to that electric field, obviously the electron from magnetic area in p move in that direction from p to n direction. Similarly, the magnetic area hole in n side similarly move in same direction of the electric field in that direction. So due to that, the electron from p side move in drift, due to drift to n side, and here you see that this hole from p side, hole from n side, hole from n side, okay, that's side, hole from n side, drift, hole from n side, drift to p side region. So this drift, the main concept is drift. We get drift due to electric field, and the minority carrier moving, minority carrier are moving. Okay, and this electric field create due to space charge region, okay, due to space charge region. There are two space charge region, positive and negative, and this space charge region create due to majority carrier diffuse, due to diffusion, create due to diffusion, and this diffusion create due to uh, concentration gradient of majority carrier, concentration gradient for majority carrier, concentration gradient for majority carrier, because that due to that concentration gradient from electron move from n side to p side, because there is a high electron in n side, low volume of electron in p side. Due to that the electron diffuse from n to p, and there's a huge number of hole in p side. Due to that lack of hole in n side, due to the huge number of hole move in the p to n region, so that's why it created some depletion region. So you get some plus and minus. These are called space charge region. The depletion region is called space charge region. The positives and there's some negative. So that's why there is some electric field. Due to that electric field, we move from minority carrier. Due to that electric field, minority carrier moving. That's our moving is called drift. This moving is called drift. Clear? So the one is called diffusion, other is called drift. These two portion is very important. So that's why you get some two current. One is drift current, other is called diffusion current. So that a PN junction current, PN junction current depends on two factors. Diffusion current first, then drift current. Diffusion for majority carrier due to concentration gradient or mismatch in two extrinsic semiconductor, and diff current we get due to electric field. Okay, now here we see that, so first, if that we see the time goes on, so more diffusion is occurred. Okay, if the more diffusion is occurred, so you see that is time goes on, so more diffusion occur. So more diffusion occur means space charge region, more number of plus here, more number of minus in that left side of the depletion region. Due to that is a more electric field. So more electric field means more magnetic area moving. So at that equilibrium, so drift current, that is also equal to diffusion current. So you get a net current with a zero. Okay, the concept is like that. So in equilibrium, we get some zero current. In equilibrium, we get a zero current. Because current from diffusion, that is equal to current from drift with the same. So you get some zero current here. Okay, because there is same current here, there's an equal. So that's very important or key point. Okay, by equilibrium diffusion current, okay, large of drift, first position drift is very small, diffusion is very high. Okay, you see the diagram, drift is very small, diffusion is very high, but time goes on, so diffuse more, so more space charge region, so more junction to be extended. If that is more diffusion means more junction extended here. So if I draw a diagram again, so draw the diagram again. So there is a p-type semiconductor, there is a junction, and that's the n-type semiconductor. Here is a huge number of hole here, and there is an electron in left side. Okay, so when the diffusion is on, okay, so here electron diffuse from n side to p side, and hole diffuse from p side to n side. Okay, so electron diffuse here and hole diffuse inside direction. So the diffusion is goes on. So this region, this space charge region, more number of hole accumulate here and more number of electron accumulate here. So these depletion region, okay, so these depletion region and these two junction, mainly these two junction shifted to left side. So space charge region is more space charge region is created. If more space charge region, so that's why the more electric field. So in that direction, so there is a more electric field. So means more magnetic area drift here. Okay, from magnetic area drift from magnetic area in p side is a electron drift in that direction, and magnetic area in n side, that is a whole drift from n to p region. So more drift current. So that's why when drift n equal to diffusion current in equilibrium condition. Okay, so that's why the whole total current, the whole means the total current with a zero in the semiconductor. Okay, in that equilibrium, no biasing apply here. Okay, so what is biasing I discuss later. So now in that diagram we see some barrier potential. So what is the barrier potential? And you see that there is a more positive here, means this side with a higher potential, and p side here there is a electron, and there's a lower potential, these are the minus, and here with a plus. Okay, so that's okay, and this distance, okay, distance is called V naught, and this is called barrier potential. Okay, so this potential actually to prevent the movement from electron from region n side to region p side. Okay, So what is the barrier potential? When asked what is the barrier potential, right here that this potential, the potential, okay, the potential to prevent uh, the movement of the movement of electron from N region into the P region. Electron from N region into the P region. Region to P region is called barrier potential. Okay, there is a higher potential, there is a low potential. The gap these two potential is called barrier potential. Okay, and these are schematic diagram. Now it look like this. This diagram, suppose, okay, and there's from depletion region. Here is a more positive, and here is negative. Okay, so now this region is called depletion region. We know that, and here these two end of that is a p type semiconductor, here is a n type semiconductor, here is a metal contact, this called is a metal contact. Okay, and these are metal contact, and here also a metal contact, these are the metal contact, metal contact, metal contact. Okay, and now electron, and here is some hole, and the schematic diagram is look like this. So P, that's the N. So this arrow represents current in moving P to N region. Current is moving. So diode current, actually these are called a PN junction diode. The diode current moving P to N region. Okay, for forward bias. So current moving P to N for forward bias. So what is forward bias? Another bias is reverse bias. What is biasing? So next class we discuss what is biasing. Okay, so today in the class here the basic idea about what is a junction and how to combine electron and so n region n type semiconductor to with p type semiconductor. Okay, so that's the end of today's class. If you have any doubt, please ask in comment section. I'll try to give the answer. So meet again next class. We discuss next class what is a biasing. That's a very important concept. Okay, so thank you.